Hello there, young students of chemistry. So in this segment, we're going to talk specifically about the equilibrium constant. And how do we write a mathematical expression that can be used to make calculations with the equilibrium constant, to figure out how much of what we have. So in the last segment, we talked a little bit about the equilibrium constant when we were looking at our graphs. And we saw that if the value for K is greater than 1, then that favors the production of products, and the equilibrium lies to the right, not right. And the larger the value for K is, the more products you're going to get. So anything greater than 1 is what we say, okay, we're going to have more products than we have at equilibrium than we have reactants. If the value is very small, less than 1, and it can get very, very much less than 1. That favors the production of reactants, and we would say that the equilibrium position lies to the left. And if the value of K is 1, we would say, hey, this reaction has no tendency. We're going to get equal numbers of reactants and products. So the equilibrium constant, although it is constant, it does change. But the only thing that will change it is temperature. So if you calculate an equilibrium constant, or if you're given an equilibrium constant, you are given that for a particular temperature at which the reaction is occurring. This is how we write what is called an equilibrium constant expression. This is called an equilibrium constant expression. It's important that you know what the words mean, so when I ask you to write one, you can write one. Equilibrium, the equilibrium constant expression is the mathematical expression that allows us to calculate the equilibrium constant. So what they're showing here, we're going to use the law of mass action to write the equilibrium constant expression. Please remember that these brackets specifically mean molar concentration, moles per liter, which is why when we're doing some stoichiometry, we can use molarity in our stoichiometric chart. In this case, we'll call it an ice chart. So what we're going to do is take the concentration of the product C, and we're going to raise it to the power of its coefficient. So if there's a coefficient of 2 in front of C, that concentration becomes squared. We're going to multiply that by the concentration of the product D and raise that to the power of its coefficient. And then we'll put our reactants on the bottom. Those concentrations also raised to the power of their coefficients. So the equilibrium constant expression is the product of the products raised to the power of their coefficients divided by the product of the concentration of the reactants raised to the power of their coefficients. These are not things that are hard to write. Getting the equilibrium constant expression, all you need is a balanced chemical equation. It's just that the calculations can get a little more complicated. So one of the things you have to remember with the law of mass action, though, is that because we're dealing with concentration, there are some things that have constant concentrations. For example, solids and liquids have constant concentrations. The concentration of a solid, another way you might think of that, you could call that density. That is a constant thing. So because solids and pure liquids, because they have a constant concentration, we don't include them in the law of mass action. We just leave them out. So within a chemical equation, if we have pure liquids, not aqueous because that's a mixture, pure liquids and solids, we do not include them in our equilibrium constant expression. So if we look at these reactions here, we can write the equilibrium constant expressions This is the decomposition of calcium carbonate, and we know that metal carbonates decompose into metal oxides and carbon dioxide gas. The calcium carbonate is solid, and so is the calcium oxide. So in this case, remember that we put the products on top, raised to the power of their coefficients. The coefficient here is 1. So in this case, it's just the concentration of carbon dioxide. So the only thing that determines the equilibrium position for this compound, for this reaction, is the carbon dioxide. Products on top, reactants on bottom. So if we look at this gaseous equilibrium in number 2, we can see that everything is, there's no solids or liquids here, so we're going to keep them. So the equilibrium constant is equal to the concentration of ammonia. That's how we read that. And we're going to square that. So the concentration of the products raised to the power of their coefficient divided by the product of the concentration of the reactants raised to the power of their coefficient. So products on top, reactants on bottom. On the bottom, we're going to have the reactant hydrogen cubed times the concentration of nitrogen, and its coefficient is 1. We have the decomposition of sodium bicarbonate in number 3. We leave out the solids. They have constant concentrations, which means we have no reactants in our equilibrium expression. Products on top, reactants on bottom. So our equilibrium constant expression is just the concentration of the water vapor times the concentration of the carbon dioxide gas. You might recognize this reaction, outside of the crazy reversed arrows, as the ionization of water by a weak acid. If we want to write the equilibrium constant there, remember that we keep we throw solids and liquids out, so we'll leave out the liquid water. The equilibrium constant expression is equal to products on top, concentration of hydronium times concentration of acetate divided by reactants on bottom, concentration of acetic acid. And you learned in the last unit that if we have concentration of hydronium, why then we can calculate pH. That's exciting stuff. This last representation is for the dissociation of a compound in water, because we have a solid dissociating into its aqueous ions. This is called solubility product equilibrium. Right? This number 4 was called acid dissociation equilibrium. But remember, we throw solids out. So equilibrium constant is equal to, oops, forgot to balance this one, the concentration of lead ion times the concentration of nitrate ion, and that concentration has to be squared. So what I'd like you to do is to take a minute, pause the recording, and I would like you to write the equilibrium constant expressions for the reactions that are presented here. I'm sorry about the arrows. That really bothers me that they're reversed. You might want to redraw them. Okay, please check your work. So what you have learned in this segment is what is the equilibrium constant expression and what does it tell us about a chemical reaction that reaches equilibrium. And you've also learned how to calculate the mathematical expression that we will use to calculate a value for K. Okay, in the next segment, we are going to start making some calculations using some concentrations and our equilibrium constant expressions that we have written using the law of mass action.